Hi, Sayed.
Hi, how are you?
Good, and you?
I'm doing good.
Okay.
I had a question about regrades.
Yeah.
Um, do the students see their booklet number? Because some of them have asked me for a regrade, but I can't find them by name, and they don't seem to have a booklet number that they can refer me to.
Um, yeah, for regrades, let me see. Let's see. So for regrades, send their send their name and student number to Waleed. Waleed will be doing regrades,
Okay,
and he has the ability to find their booklet based on their name and student number.
okay.
Um, okay. Okay, let's let everyone through.
Okay.
Morning, everyone.
Good morning, sir.
Morning, everyone. Okay. Okay, so there is not going to be a quiz today. However, I want everyone to register at this site. And when you do register, you should use your uToronto email. If you do not have one yet, which would be really strange, but anyway, if you don't have one yet, then use whatever email you can. And then the enrollment code for MAT240 is this. Just be patient. If it's not loading, just wait for a second. Okay. Yeah. So so if you haven't already gone to the site, don't go on it yet. You can do it later. Okay. So just wait. Do it later today. It's not important to do it right now. But the site is, yeah, up there. Okay, so let's start. I'll take a couple of questions. If there's anything right off the bat.
I had a question. So I had a question. I was asking other people about this.
Go ahead. Go ahead.
What is a linear subspace?
We're going to get to that today. Yeah.
Okay, that's what we're getting to today. Okay, cool.
Yeah. Anything else? Anyone? Okay. Let's start, and then okay, so for some reason okay, I got it. There it is. Okay. Very good. I just need to be able to see a few people in the class at least. Okay, so we talked about the main object of study for this class, which is the mathematical structure of a vector space, which is it involves two things. You have to decide, first of all, what your field is before you even talk about a vector space. You have to decide what your number system is. And once you have the field set, then what we need is another set, V, which is usually called the vector space. So a vector space is really all this information. It's the information of a field together with all of its structure and axioms, together with this other space with its structure and axioms. So technically, a vector space is all of that data. You could think of it as like a tuple where you list all of that stuff, f plus 0, and so on. But just for brevity's sake, we just refer to this set V as the vector space when we kind of know what the field is and so on. And the point is that we have an abelian group structure, so we have a commutative associative addition with unit or additive identity, and we have additive inverses. Okay, but the other thing that we have is this remarkable structure, this scaling structure. Okay, and this scaling structure is required to be compatible with the field and with the structure of the abelian group on V. So we saw all of this, and I went through some of the simplest examples of vector spaces, the zero vector space, the field itself, which is kind of like, you can think of it as just a number line. And then we can take products, Cartesian products of the field with itself. So F product F is giving us a two-dimensional vector space, and we can continue taking products like that. And we even saw this example, which was a discrete vector space, because the field that we're using is discrete. It's just 3 points. And so we ended up with this plane, this kind of two-dimensional plane, but in the discrete sense. So we have this grid, the way I drew it. Okay, and then you can continue this process and take higher powers of the field. And so in a way, the elements of this vector space, the vectors in it, are just n tuples of numbers. Okay, and so we're kind of rapidly getting into higher dimensional vector spaces. Okay, and then the other thing that I wanted to point out was that there's not much difference between the Cartesian product of the field with itself n times and the polynomials, because a polynomial, you could think of x as a placeholder variable, and you could think that the purpose of having that x there is to separate the different coefficients, that this is the coefficient of the 0th power of x, and this is the coefficient of the first, and so on. So really, what a polynomial, you could think of a polynomial as just a list of elements of the field in order, right? So it's an ordered collection of elements of the field. But how long is that list? Well, that's the difference. That in this case, the list has length n, but in this case, the list can have any finite length. So a polynomial is essentially a list, a finite list of numbers, right? But the length of the list is not prescribed. Okay. Now, I want to point out one warning, a big warning fact right here. Okay. And actually, I even would say that that the textbook has a problem with this. Actually, many textbooks do, because the textbook says that a polynomial is a function, and this is something that you learned in high school. That you think of a polynomial as a machine that takes an input number and does some process to it, which involves multiplication and addition, and then outputs a number, right? So you think of it as a map. So sometimes, we may sometimes view a polynomial as a map from the field to itself, right? And so if p of x, so if p, the polynomial p, let me use the notation. So let's say I have f of x, this is the polynomial ring, and say I have an element p in it. Okay, that element p, it can always be written as above, like this. For some n. Okay, and this defines a map. It does define a map, it's true, which takes an element in the field and sends it to a0 plus a1 multiplied by x, x being an element of the field now, not some weird variable or some formal symbol. So now here, this is multiplication in f, and this is addition in f, right? And we just add up these numbers, an, x to the n. Okay, so I want to make a distinction, okay, between the polynomial as an object, as an element of the polynomial ring, where we think of x as a symbol, okay, some kind of formal symbol, right? I want to make a distinction between that and the idea that the polynomial defines a function from the field to itself. Okay, so and the reason why you don't make that distinction usually is because usually when you use the real numbers, so if f is the real numbers, there is no there's no real difference between viewing them in one way or the other. There is no we are not losing anything by thinking this way. So this is valid. So it is valid to define polynomials as functions of this type. Okay, but if the field, for example, is what we called F2, or maybe I called it Z2, okay, the field of two elements. What two elements does it have to be? Well, the field with two elements is really simple, because if you look at the definition of field, you see that there's always at least two elements in a field, 0 and 1. So if the field only has two elements, then it's got to be those two elements. So if the field has two elements, 0 and 1, right, you can easily see what's going to happen here. So for example, if I take the polynomial x squared plus x, suppose, this is a perfectly good polynomial. So this means, what does this mean? The coefficient in front of x squared has to be an element of the field. So here the coefficient is 1. It's the multiplicative identity in the field. And here as well, the coefficient is 1. And the coefficient is 0 for anything else, like the constant coefficient, for example, is 0. Okay, but so this is a perfectly good polynomial. It's an element of the polynomial ring, and this is not the same as p equals 0, the 0 polynomial. Okay, this is the additive identity in, this is the identity in f2x. It's the polynomial that when you add it to any other polynomial, you don't change it. Okay, but if you think of it as a function, okay, from the field to itself, well, what happens? 0 is sent to 0 because 0 squared plus 0 is 0. And 1 is also sent to 0 because 1 squared plus 1 is 1 plus 1, since 1 squared plus 1 is 1 plus 1 is equal to 0 in F2. Okay, so this polynomial is a non-zero polynomial, but it defines the 0 function. Okay, so these two polynomials determine the same function, even though they're not the same polynomial. So in a way, the map from polynomials to maps, okay, is not injective. The map taking polynomials to maps from the field to itself, oops, sorry, is not injective. Because you can have two polynomials which determine the same map. Okay, any question about that? Okay, so I'm trying to give you a new viewpoint compared to how you normally think of polynomials. You should think of them in this way, and you should disregard or rip out the pages of the textbook where they say that the polynomials are functions or maps. Okay, any questions?
I think Jay has a question, but I think it's before this material.
Yeah, it was before. Yeah.
Okay, go ahead.
Oh, okay. So like this pertains to when we were defining what a vector space is and using some field. So you know how we have dimensional analysis, right? In physics, the left side of some units has to be the same units on the right side. So
yes,
when we can define as a vector space as F or the Cartesian product of F,
yes,
but F is a field and the vector space itself we defined as some abelian group. So
Yes.
how are they even necessarily equated? Like, I might just be thinking about it wrong, but like the quote unquote, there are different types of
Yeah.
like sets.
Yeah.
So how are they equated?
Indeed, what you're saying makes perfect sense. So the point is that the way that it works, okay, is that when you view like here, so when you view the field itself as a vector space over the field, okay, you need to decide what your vector space is. So you have to decide what the field is. The answer is F. And you need to decide what V is, what the second set is. Okay, so that second set is supposed to be V, is supposed to be an abelian group, okay? And then we're supposed to have an additional structure. So the question is, what is going to be this set? It's going to be this set, which is part of the structure of the field. So technically, I'm taking the field, which is all this information, and I'm forgetting a whole bunch of stuff. I'm discarding this, this, and this. I'm only going to remember the first three structures involved in the field, and I'm going to put them here. Well, the inversion also. Okay, so this is called forgetting. Okay, it's actually a technical term. You take a structure and you forget some of the structure. Okay, forget some of the structure of the field, and you make it only into an abelian group. Okay, so that's the first step. Is that I know, well, the first and second step. So I know that the field is F. I know that the vector space is F as well, but with some of the structure forgotten. And then I need this binary operation from F cross V to V. And I use this, the multiplication on the field. I use it for this purpose. Okay, so in a way, you're using parts of the structure of the field for different purposes now. And that's how it goes.
I see. Thank you.
You're welcome. Okay, so right. Okay, another example of a vector space. I don't know what we're on to now. We're 5, 6. Example number 6. Okay, it'll be what we'll call F infinity. So this is the set of lists where the entries on the list are elements of the field. So they look like this: x1, x2, and so on, where such that the xi are numbers in the field. Okay, so this is now, you could think of them as sequences or infinite lists. Okay, and what is the difference between this vector? Oh, and I should say, so this is an abelian group addition inside V is component wise. And the scalar multiplication is just lambda multiplied by a list is just lambda x1. It's again component wise, lambda x2 ... Okay. So this is giving us, this is another example of an infinite dimensional vector space. Again, we're going to talk about dimension properly later. Okay, but I just want to point out that this is not the same as the polynomials. The polynomials are also sequences, A0, A1 up to AN. But the difference is that the polynomials, the sequences are not allowed to be to be to have they're not allowed to be infinitely long. The sequences can only be finite length, but the length is unbounded. So they're both infinite dimensional, but they're different. They're different as vector spaces. Okay. So the main topic that I wanted to talk about today is subspaces. So I'm going to move on to subspaces now. Are there any questions before we move away from the examples of, actually, I want to talk a little bit more about the examples.
Sorry, can I ask a quick question?
Yeah, go ahead.
How is the polynomial vector space infinitely dimensional if the sequences are finite lists?
Well, I'm just trying, so, your question is undefined because we haven't talked about dimension, okay? But just intuitively speaking, right? If you had polynomials only of degree 1, you would only have of degree, look, at most 1, suppose. Suppose we looked at polynomials of degree at most 1, then it would be all things of the form a0 plus a1x, and it would terminate here. So that would be 2-dimensional, because it's like f squared. Okay, but if you allowed polynomials of degree less than or equal to 3, or less than or equal to 2, I'm sorry, if it was less than or equal to 2, then you would have a0, a1, and a2, and that would be 3-dimensional, right? So what dimension do you think it is? If you think it's n-dimensional, then I'll just take polynomials of degree n plus 1, n plus 2, n plus 3, right? Polynomials don't have any maximum degree, right? So when you consider all polynomials, they can't fit inside just n dimensions for a fixed n. Okay. But this is intuitive reasoning. We're going to get to prove that these facts are true. So, right, the last thing I wanted to say about examples, so there's another important, really important class of examples, and these are function spaces. Okay, so the idea of a function space is the following. So let X be a set, okay, and F a field. Okay. Okay, then we can consider the set of all functions of all maps from X to F. Okay, so this is the set of all these maps is denoted in the following way. It's a bit confusing the first time you see it. It's like this, F to the power X. So again, F to the power X is the set of all maps from X to F. So they're kind of like, they're numerically valued maps. So they're functions. They take values on every point on the set X. So for example, temperature as a function on the planet Earth is an element, is such a function to the real numbers. Okay, and this this has the structure of a vector space over F. So how does this work? So if I want to define, so first of all, we have the 0 function. Is the function taking value 0 for all points in the domain. Okay, and the addition law f1 plus f2 is the function taking x to to the sum of the evaluation of f1 at x and the evaluation of f2 at x. And this is the sum inside the field. Okay, it's what you normally know about functions, right? That you can add functions. It's nothing special. If you take the 0 function and add it to a function, you're not changing the function. Okay. And then finally, the scalar multiplication, right? If lambda is in f and f is in x to the f, oops, sorry, I made it f to the x, right? Then this is the function which takes x to lambda multiplied in the field with the evaluation of f on x. Okay, so I'm defining the function by telling you how it maps every single possible element in the domain. Okay, so remember, just as an example of this, okay, remember that we had these very nice sets Bn, which is the set of n first counting numbers. Right, this is like the natural set of cardinality n. Right, so if we take f to the Bn, we get the set of maps from Bn to f. So what are these functions? Well, the function takes values on the number 1, the number 2, the number 3, right? So in order to know one of these functions, you need to know only, the only thing you need to know if you want to identify one of these functions is what its value is on 1, what is its value on 2. If you know the values of f on all the first n numbers, then you would know the function, right? So, so f can be written exactly as a list of its values on 1, 2, and then up to n. So in other words, you just put them in a list all the possible values of f. Okay, and what you see is that this is an element in f to the n. Okay, and this is the reason for the notation f to the x. Okay, you see that when I use the standard set of size n, f to that set is the same thing as f to the n. Okay, so so this means that f cross f, the vector space that we studied before, right? This is an example of a function space. Okay, we can think of it, can view it as the functions on the set B2, right? So functions on the set B2 is exactly the vector space f cross f. Okay, so normally you think of the plane, let's say with r cross r, if the vector space is r cross r, right? You think of the plane as in a kind of geometric way as a flat plane, okay? But you can also think of V as the space of all possible functions on 2 points, right? So this, here I'm describing a point in V, and this function, which I'm graphing here, where the domain is just 2 points, this represents the same information. It's giving you 2 numbers, just like this does. Okay, so you can, oftentimes there's many different ways of understanding a vector space. You could sometimes think of it geometrically as a actual space, or you could think of it as function space, and there's many other ways of thinking of it. So in the assignment, there's a question which asks you to study something about the functions on the real line, and that's what this notation r to the r means. R to the r, right? This is saying that the set X that we're using for our function space is the real line itself. And this would be the set of all functions on the real line. This is just yet another example. I just wanted to kind of give you a preview. Okay, so now I really do want to get to subspaces. Okay, any questions about the idea of function spaces?
So Gurmanjot has a question, but I think it's before function spaces.
Yeah, I was just it was just sorry. I
Go ahead.
Okay, so in terms of polynomials, you're like you're talking about how they only have a finite set of coefficients. So I was just wondering, like, could you not represent polynomials in terms of an infinite sequence of coefficients where all like Cn plus 1, Cn plus 2, etc. are just equal to 0?
What do you think?
Similar to a power
What do you
series?
think? What do you think?
Well,
What do you think?
Well, yeah, obviously,
Yes.
I was just wondering, like, in that sense, it would be
Yes,
like,
yes. You know perfectly well that you can. Yes, of course.
Okay,
You could
just
think of it
making sure.
as a sequence where you have only finitely many non-zero elements.
Okay.
Right?
Okay.
That's what a
Thank you.
polynomial is. It's a sequence where you have only finitely many non-zero elements.
Okay.
Go ahead. Is there another question?
Yes, Omar. Oh, okay.
Yeah, it was also from the past about polynomials.
Okay.
So just to get the right idea of a polynomial, so in this case, a polynomial of, let's say, like x to the power 3.
Yes.
So like we have a0, a1, a2, a3. Those are considered the elements, while x and x squared and x cubed are just notation for their position. Or I'm not.
So this is the notation for the polynomial ring. Okay, it is a set. What is inside that set? Polynomials. The elements of this set are polynomials. What does an element look like? It looks exactly like this. Okay, in order to write down an element of the polynomial ring, you need to decide what n is. You need to decide what these values are inside the field, and then you write this expression. This expression here is a polynomial.
Okay, so it's okay. So my idea of it being
so one way to think about it, okay, one way to think about it, and I'm not changing it in any way. You can think of it as a finite sequence of numbers in the field. That's what it is. You just have to put them in this order like this, and you use x power, power I to denote the I+1 entry in the list. So it's a finite list of numbers placed in an expression like this. What's the point of you writing this expression like this? Is that it makes it much more obvious how you should multiply them, how you should add them, and so on.
So in other words, a0 plus a1x can be written as a list of a0, comma a1.
Yeah, correct.
All right. Thank you.
You're welcome. So what about function spaces? No questions about that?
Sorry, Professor. I have a
Yeah,
question about function space.
go ahead.
So I want to ask how to how to imagine the function space as the two dimension x and y. So I feel confused about the conversion. Like how the function space can be the point of the coordinates.
The way is that, if you have a function, okay, which is defined on just 2 points, okay, then how do I, if you wanted to tell me, let's say we had you and I, right, are 2 points, and each of us has an age, right? So you could just write You could just graph the function of age. This is your age and this is my age, right? So that's two numbers. Okay, but you could also graph it by taking the age of me or the age of you on one axis and the age of me on the other axis and drawing a point. So you could think of a point in the plane as telling you what the two ages of the 2 points are, of the two people are, or you could just think of it as a function on the space of people.
Oh, okay, understand. Thank you.
Okay. Anything else? Just I'll take one more question about function
Hi,
spaces.
Professor.
Go ahead.
Hi, Professor. So can we say that Fn is equivalent to the function space Bn?
Yes, this is the same thing. Yeah, that's right. So this argument means that f to the Bn is equivalent, is the same vector space as f to the n. Okay, the reason that I'm explaining this is because it explains the notation. That's the reason why the function space is sometimes written this way, as maps from the set X into F. It's because of this fact, that if you use the standard set of n elements, you just get Fn. Okay, we need to move on. I wish that we had more time. Somehow I find that these online classes, it's like time seems to move faster than in the classroom. I don't know why. But okay, so subspaces. So let's say that we have a vector space. Let V be a vector space over the field F. Okay, a subspace, and I just want to use the term a linear subspace. Most of the subspaces that we're going to study in this class are linear subspaces, and so we may not always say linear subspace, but they are, yeah, the standard terminology is a linear subspace. A linear subspace U inside V is a subset of V, okay, which inherits a vector space structure from V. Okay, so what does that mean? So you need to check that you see the operations and the structure of V. Okay, so remember that we had this operation which takes two things in V and spits out something in V, right? We need to make sure that if you restrict this to U, and if you take two elements in U, that the result lands also in U. That's called being closed under addition. The other thing we need to make sure is that the origin is in U, okay? And that the inverses are in U. And then we need to make sure that if this element is chosen in U and we multiply it, we do scalar multiplication, that should land in U, okay? And again, just like before, in order to prove that the subspace is a vector space, we don't actually need to check the compatibility axioms, because the compatibility axioms already hold in V. Okay, so this means that i.e., and this just means I'm going to explain what inheriting means. It means that 0 must be inside U, okay, and that if U1 and U2 are in U, then we must have that U1 plus U2 is in U. Okay, and also if lambda is in F and U is in U, then lambda multiplied by U is in U. Okay, now remember that I said all the structure should be there. So technically you would have to check that the additive inverse of something in U must be in U. So do we have to check that additive inverses are in U? And the answer is no, since the additive inverse of any vector v is -1 in the field multiplied using scalar multiplication by v. Okay, so if you know, so this is one of these elementary facts that follows from the axiom that if I take any vector and if I add it to -1 multiplied by v using the scalar multiplication, then I will get the origin. And this follows from the axioms. You should check this. Okay, so what that means is that once I've checked that U is closed under scalar multiplication, let me give the names of these. This property means that, so the fact that the left side implies the right-hand side means that it's closed, U is closed under addition, vector addition. And this fact is that U is closed under scalar multiplication. So it turns out that being closed under scalar multiplication automatically implies that the additive inverses of the elements of U are in U already. Okay, so that's all that we need to check, and the axioms hold automatically. The axioms hold since we assume they do in V already. Okay, now so let me explain some ways of getting subspaces, how to build. Well, okay, let me first give some examples of subspaces. Okay, so subspaces, examples. Okay, so suppose that we look at the simplest, well, this is maybe not the simplest, but let's just look at R. Okay, what are the subspaces of R? Well, we know that the subspace has to have the origin. That's the most important thing. And it must be closed under addition, and it must be closed under scalar multiplication. So if we just take 0 inside R, this is a subspace. Okay, it's the minimum that you could have. Certainly the origin is in there. The sum of the origin with itself is the origin, and scalar multiplication is again the origin. So this is a subspace. Okay, and the point is, what if the subspace had another element? What if, if we include another element, let me call it R, something which is not 0, into U. So i.e., if U contains 0 and R, which is not 0. Okay, then what else must it contain? Well, it has to be closed under addition. So that means it must contain, so let's say R is here. Okay, so if it contains R, it's got to contain all sums that involve R. So it must contain also R plus R, R plus R plus R, and so on. So it's got to have all of the sums of R with itself that must be in the subspace. Okay, but it must also contain lambda multiplied by R for all lambda in the real line. So this is a vector space over R. And I'm allowed, if R is in the subspace, then it must contain all scalar multiples of R. So that means that if I multiply R by -1, by -2, by -3, if I multiply R by 1/2, okay, if I multiply R by any real number, that should be included. So that means that I'm going to get every possible number in the subspace, okay? And so this implies that the subspace must contain all R. So this means that U must be R, okay? So we have two possibilities. Either the subspace is just 0, or the subspace is the whole real line. So there are only two subspaces of the vector space R, 0 and the whole space, okay? And this is a very special fact about dimension 1. Okay, so now let's look at the second example. Actually, this was this example. So what if we do R2? Okay, so the same thing goes. So number 1, the simplest subspace is always going to be 0. So 0 is there. It's always a very pleasant 0-dimensional subspace. Okay, but what if a U, so if U contains some other vector, not 0, so let me draw it here. Suppose that I have some vector V. Okay, so if I have the vector V in the subspace, I must have all sums of V with itself, and I must have all scalar multiples of V. So as a result, this will allow me to get all multiples of V. And so what I'm going to get is a straight line passing through the origin. The set of all lambda multiplied by V, where lambda is in R. Okay, it must contain this, and this thing is a straight line through 0, 0. Okay, and this this line, which we obtained by taking all multiples of V, is called the span of V. This has a name. It's called the span of V. Okay, this is the span of V. Okay, so so these are all subspaces. So that means that we have a very large number, infinitely many subspaces like this, because we could take any vector at all, and we'll get a straight line through the origin. So each of these is a linear subspace. Okay, so now we have a whole bunch of these, and I just want to point out that it's not enough just to have a straight line, right? If I drew a straight line here, okay, this is straight, but it doesn't pass through the origin. It's not closed under addition. This does not include 0, and it's not closed under plus or scalar multiplication. Okay, and the last thing I want to point out before we close for today, okay, is that if, so suppose that we have, suppose U, this is the third possibility, suppose U contains V, which is not 0, and suppose that it contains one other element, one other vector, W, which is not in the span of the first vector. Okay, so I need to choose another vector, W, okay, which is not on the span of V. Okay, and in that case, okay, U must contain all elements, sorry, all elements of the form lambda 1 times V plus lambda 2 times W, where lambda 1 and lambda 2 are in R, right? So what does that mean? So first of all, I need to have all, if it contains W, it's got to contain 1/2 W, twice W, and so on. It has to have the whole line passing through W. But then I also should be able to take the sum between V and W. Sorry. If I take the sum of V and W, it'll be there. And I should be able to scale that independently with lambda 1 and lambda 2. So I should be able to take, a larger proportion of W, a larger proportion of V, and so on. And so this point could occur here, 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 right? And what you can show is that all points will then be in the subspace. So this would imply that all points in R2 lie in U. Okay. This is also called the span of the list of the vectors that we used. The first one was V, and the second one was W. The span is the set of lambda 1 V plus lambda 2 W, where lambda 1 and lambda 2 are chosen to be in the field. Okay, and so what I'm trying to illustrate here is that every linear subspace is on this list. It's either got to be 0, a line through the origin, or the entire plane. And those are the only possibilities. And in the assignment, you're asked to also investigate these linear subspaces for a couple more examples, which are actually, well, they're finite, so they're easier than this. Okay, I'll leave it there for now. Have a good weekend, and office hour is starting now. So let's just have questions, and it could be about this. Maybe we should start with questions about today's lecture, and then later we can talk about other things if you want.
Okay, so GCow has a question.
Sorry. Can you first go to the definition of subspace? You wrote down 3 things. So doesn't 3 imply 1 here?
Yes, that is true. Yeah, that is true.
So
3 implies 1.
Okay.
Because why? Why does it imply 1?
Well, because 0 is a valid lambda, so you can just take 0, multiply U, then you can get 1.
That's right. So there's a fact, a lemma, which is that if you take 0 in the field and V inside V, then the scalar multiplication of 0 with V is equal to the 0 in V. Okay, so you need to prove this lemma. Easy to prove, but it's true.
But does that, yeah, okay. So I was wondering, does that, it takes into account the assumption that U is non-empty, right? I mean, if U was empty, then we can't say that, I guess.
That's right, yeah. So you do want to make sure that there's at least one element in U. So technically, yeah, that's That's right.
I see. My second question is about the span of W. So you mentioned that span of V has to contain the point 0, but it looks like span of W doesn't have to contain.
What do you mean
the
by a
origin.
span of W? You mean the span of only one element? The span of just, instead of looking at span of V, we take span of W? What do you mean?
So previously on the left-hand side, you draw a red line, and then you mentioned this one doesn't include 0.
Yeah.
So I was just wondering, this line can actually be a W.
I'm sorry.
Or
I don't understand your question.
I guess, does that mean span of W has to contain origin?
What is W?
W is just another vector that's not in span of V, right?
Okay. Can we take W to be an element of the vector space?
Yes.
Okay. So what is the span of W? What is the definition of the span of W?
Well, it's just another lambda times W.
No, the way that you're phrasing it is not quite right. What is the definition of the span of an element of the vector space? It is a subset which consists of all scalar multiples of that element.
Okay. Yeah, I can see that. Yeah, I understand my question now. Thank you.
Okay, you're welcome.
Okay, so Dikshant has a question.
Yeah, so my question was with the function spaces, like, I don't quite understand the, so when we say a function space, is the function over here the polynomials that we're referring to? Is it the field of polynomials over F?
Sorry, what are you talking about polynomials? There's no polynomials here.
So when we say function spaces, what is the function?
Okay, so if you have a set, right? Like the planet Earth, let's say.
Okay.
You can consider functions on that set. Things like the temperature. The temperature is a function. It takes a numerical value at every point on planet Earth. It is a function on planet Earth. It is a map from the sphere to the real line, the real numbers.
Okay.
That is one particular function. The temperature now is one function. The temperature tomorrow is another function on the sphere, which takes numerical values. Okay, so any set you could take, you could take the set of keys on a keyboard, right? What is a function on that? It's assigning a numerical value to every key. That's one, but you can do that in many ways, right? You can assign to one key, you could assign the number 15, or if you wanted to consider a different function, you could assign the number 28, right? These are different functions on the same underlying set. And if you consider all such functions, then that forms a vector space.
Oh, okay. So these functions, we don't really, so it's, okay, yeah. Okay. I think I get it. It's very abstract.
Well, I mean, I don't know how abstract it is. If you give me 1 point, then what are the possible functions on 1 point?
Well, like that point to another, I don't know, like.
Give me here's a point, I'll call it A, okay? It's a single point, A. Give me an example of a real valued function on this point A. Give me one example of a real valued function on the point A.
Like, do you mean like f of A would give you something else? Like
Just
that kind
give
of.
me an example of a function. What does the function, if I evaluate the function at the point A, what will I get?
Let's say you get 1, a real number 1.
Okay, and give me another example of a function on the set A. You gave me one by saying the number 1. Okay, what about another different function? Give me another one.
F of a equals, like in the same real numbers, or
Yes, yes.
F of a equals 2, 3, 4.
Okay, so what is all possible functions on the set of one element?
All the real numbers.
Yeah, that's right. So that's what I'm saying here. All functions on a set of n elements is the same thing as f to the n. It's like just giving a list, right? If it was only one point, then the list would just have one number on it and we would just have the field. But if it has 2 points, then to know the function's value at the 2 points, we need a list of length 2 to know its values on the first point and on the second point.
Okay.
I mean, you have a whole set of stocks, okay? All the different ticker symbols, right? That's a set. It usually doesn't change very fast. It's a set of all the companies. And each one of them has a numerical value associated to it, right? So the stock market is a function. It's an element in this function space. And that vector in this function space moves around. That vector changes in time as the different stock prices change, right? So the value of the market at one point in time is a function in this function space. So it's a vector in a very high dimensional vector space of the same dimension as the number of companies.
Okay.
I don't know if that helps, but yeah, it's very abstract. Okay, next question.
All right, so Charlie has a question.
Yeah, so this is about, again, about like function spaces. What was it called? Function spaces?
Yeah, okay.
Yeah, so
function spaces.
Could you just, sorry, I don't want to stop you from drawing your picture.
No, go ahead. I'm listening. I'm listening.
So if you have like, what is it? Sorry, I kind of need, could you scroll back up just because I wanted to.
Oh yeah, sure.
Sorry.
Function spaces, yes.
Yeah, so you have like, say so you have like f times x as an example of a function space. So if you took r times r as your function space,
Sorry, what is the
not
set
r times r.
And what? In order to know a function space, I need to know two things. I need to know what is the domain set and what is the field. So you tell me, what's the domain set?
So the domain set is all the real numbers.
Okay. So the domain set is R. Okay. And what's the field?
That's where I'm a little confused.
Well, what field do you want? You can pick any one you want.
The field of, I don't know, like 5 values, I guess. I don't know.
F5?
Sure, F5. Or how about FR?
F5. I'm sorry?
How about FR actually?
What is FR? What does that
like
even
F
mean?
of the real numbers, like that's your amount of, that's your.
Sorry.
I don't know if that's.
I'm just forcing you to use the right language. So I need to know what the domain is, and you told me it's the real line.
Yeah.
And then I ask, what is the field? Okay, the possible answers are for you, the rational numbers, the real numbers, the complex numbers, or FP for some prime P. That's what you can answer.
Okay, so then let's go with like the real numbers.
Oh, okay. So we want to use the real numbers for both. Okay. So this is, you agree that you see the notation, right? This is a set. What are the elements of this set?
Right.
I call it V. What are the elements of V?
The elements of V would just be all real numbers.
No, wrong.
Or they would be the, what is it? I guess the list of
just look at the definition of V. Okay, I have a domain and I have a field. What is V consist of? It consists of these things. What are these?
Functions.
Yeah, maps from X to F.
Right. So where X is R in our case.
Yeah, and F is R, the way you said it.
Okay.
So what is the vector space consist of?
The vector space would consist of vectors in an R-dimensional, like.
Forget about dimension. I'm asking you, what are the elements in there? This is a vector space consisting of what?
Functions.
All
In-
functions from where to where?
Functions from R to R.
Yeah, functions from R to R. So all possible functions from R to R. This one, this one, this one, right? All possible functions from R to R are
Yeah.
elements of this vector space.
Right.
Does that help?
Yeah.
This is a function. Right? It's not continuous. This is a polynomial function, right? Sine. These are all possible functions, right? All of these are vectors in the vector space. Okay, it's hard to think of it as a space because it's a very high dimension, infinite, right? So it's difficult to think of these functions as vectors, but you can think that there is an origin. The origin is the 0 function. Okay, that's the origin of this huge space, right?
Yeah.
And if you give me a function like sine, then that sine is a vector in that space. And then you have
Right.
cosine, which is a different vector in that space. And then you can take sums between sine and cosine, right?
Right. And so if you go, sorry, if you could just go.
I just want to illustrate this. So there's the 0 function, right? There's sine, the sine function. There's the cos function. There's, the function x squared, right? All of these are vectors in this huge vector space of all functions.
Right. Okay.
Yeah.
That makes sense. So if you go, sorry, could you just go back up to the,
Yeah.
I just,
Subspace.
okay, so you see that, so the point where you were trying to illustrate f to the bn, so, or f to the
yes,
2, and
f
you
to
would
the
see,
n. Yeah.
so if you took a point on the two-dimensional plane and then you expressed it in terms of 2 different points on that plane where you have.
So just 1 second. So what did I take as my domain and what did I take as the field for this example?
You took R as your domain and you took the field F2.
No, I didn't take R as the domain. This is misleading, let's say.
Or R.
The domain is B2.
Oh, okay.
It's just difficult to draw because it's just 2 points.
Right.
The domain is written here, Bn. So it's only n points, 1, 2, 3 up to n.
Okay.
Right. So if the domain is only 2 points, then in order to know what function we're talking about, I need to give you the value on the first point, which is a number, and I need to give you the value on the second point. So it's just 2 numbers. That's what these 2 coordinates are.
Right.
This is the coordinate on. This is the value on the first point, which I labeled 1, and the second point is labeled 2. So here, what we have is the ordered pair f of 1 and f of 2.
Okay, that makes a lot of sense. And so if you took, say, f to the 3, you would have a 3 and you represented it like how you did there.
F to the what?
F to the B3.
Yeah, f to the B3 would be functions on what domain?
On the domain of B3.
Yeah, B3, which is B3. It's important that it's a canonical set of 3 elements. Sorry, what I mean is that it's ordered, right? It has a value. It has elements 1, 2, 3, right? But they're labeled by the numbers 1, 2, 3. So that means that you can go and look at them in order. You can say, what's the value of my function on 1? What's the value on 2? What's the value on 3? And that's how you can make a tuple like this, which then you can think of as a point in R3.
Right. Okay.
Right? But it's very important that in order to get a tuple like this, you need to know which order to put it in. And so it's important that the domain has an ordering. If the domain was just R, G, and B, right, then the functions on R, G, and B, right, like we did this before, the functions R, G, colors are maps from the set RGB to what? To B 256, basically. Actually, it's not quite right because they index it from 0 to 255, not from 1 to 256. But anyway, it's the same idea. So we have these maps like this. Oh, I'm sorry. What am I saying? Sorry, everything I just said is wrong. What I meant was, well, the problem is that the numbers from 1 to 256 don't form a field. So it doesn't really make sense to talk about the vector space of colors. But if you, let's say like infinite precision RGB colors are maps to R, let's say.
Mhm.
I mean, it's a bad example, sorry. But,
No worries.
but the point is that the problem with this is that you would like to say that this is the same thing as R3, but the problem is that you need to decide what order to put the domain in. Because in order to,
Yeah.
you know, I need to put, like, in which order should I put it down in? You know, should I put R first and then G and then B? So with B3, you avoid this problem. B3 is already ordered. It has 1, 2, and 3. And so that's why functions from B3 to R, right?
Okay.
Each function from B3 to R can be given by just expressing its 3 values, F1,
Right.
F2, and F3. And then we get a
Okay.
point in R3.
That's cool.
So we get a bijection basically between, there's a bijection. There's a natural bijection from R to the B3 to R3. That's what I'm saying.
Okay.
Which takes F and maps it to the ordered triple F1, F2, F3. Okay, that's what I tried to denote, you know, by taking the 3 points. You know, this is one interpretation, that we just have a function that takes values on 3 points. But the other interpretation is that we make a 3-dimensional space and we draw a point in 3D.
Right. So the first interpretation is more useful once you hit, I guess, technically 4, but 3 dimensions or higher, because drawing in 3D space with 2D space is not easy.
Yeah, I mean, we're already only drawing in 2D space, and I'm
Yeah.
trying to draw 3D and 2D. So, well, okay, I mean, I could try to draw any dimension in 2D, but you're not going to understand it.
Right. Okay.
That's why we don't usually draw, you know, the stock market as a vector in, you know, 1,000 dimensional space and show it on TV. We usually just show a list.
Yeah.
The
That would be
list
very
is this
useful.
interpretation.
I think maybe aliens would like it though. Higher dimension aliens. Okay. Yeah.
Okay, there's still more hands, lots of little hands there.
Sorry for taking up so much time, but
Go ahead.
yeah.
So Omar, I think you're next.
Yeah. How do we go about, like, you mentioned that R to the R would be, the 3 possible subspaces of R to the R would be
Not
0.
R to the R, not R to the R. I was just talking about R2, just regular old R2.
Oh, sorry, R2.
Yeah.
Yeah. So these are the 3 possible subspaces.
Yeah, you've got the origin, you've got lines through the origin, and there's plenty of those. And then you have the whole space, yeah.
The whole plane. Okay, so mainly 2 questions. How do we go about proving the third point, the third subspace?
Right. Yeah, so, well, think about how you would do it. So you know, if you take a vector, which is not 0, and you produce the span, then you're going to get this line, right? You're going to get all multiples of that vector. Then what you do is you take another vector, which is not there, not in there, W, and you add it in, and you take all possible combinations between V and W. Okay, so then what you need to show, if you want to prove that this subspace is all of R2, then what you need to prove is that if I choose any vector in R2 at all, any vector AB, you need to prove that any vector AB can be expressed as a sum like this. You need to be able to find, you have to solve for lambda 1 and lambda 2 so that when you take the sum of these two things, you get AB. We're going to be doing a
So-
lot more of this later on, but what you need to show is that there exists real numbers lambda 1 and lambda 2, so that if I take this multiple of V and this multiple of W and add them together, I will get this AB that I chose. And this has to be true for all possible AB, right? So how would you do it? Well, you know, let me clean up the picture 1 second.
Algebra?
So suppose,
Or
just 1 second. Suppose that this is R2. Usually you draw the XY axes. Okay, and if I have V and W, okay, so, you know, V is going to, oops. V is going to have a span, which is this line, right? And W is going to have a span, which is this line. So this is the span of W. This is the span of V. Is that clear to everyone? What I mean by span? You take all constant multiples. You're going to go through the origin because 0 times it is there. Okay, and then if you take, and then what you want to show, the question is, so if W is not in the span of V, prove that the span of V and W is all of R2. Okay? So what is needed here? So that means to show that this is true, to show that this set is equal to this set, we need to show that every element here is in here, and every element here is in here. Okay. So to show this, we need to show that there's a containment that way and that way. Right? Now, one of these is very easy because what's the definition of span? It's just the set of all expression of all vectors which are of this form. Well, in this case, it's in R. Okay, so if you take something in here, it will look like a sum like this. This, by the way, has a name. This is called a linear combination. Of V and W. Okay, whenever you take elements of the field and you multiply by each of the vectors and you sum it up, that's called a linear combination. And okay, so if you take one of these linear combinations of V and W, take one of them, well, it's obvious that this is in R2 because R2 is a vector space. V, W are in R2. Lambda 1 V is in R2. Lambda 2 W is in R2, and the sum is in R2. So it's clear that this inclusion is clear from the fact that these operations are defined on R2 and they have output in R2, right? So the inputs are in R2, the output is in R2. The problem is to prove this one. This one is the one that requires an argument. Okay, and so what you need to do is say, let AB be any, let's say that we have some point AB in R2. I need to prove that AB is contained in the span of V and W. So this means that we must find, so let AB be in R2. Okay, we must find lambda 1, lambda 2, such that the linear combination is equal to AB, and therefore AB will be in the span. Okay, so the question is, if I give you a point in the plane like this, and we have V and W like this, how do you figure out what multiple of W plus what multiple of V is going to equal this pink point?
Represent them as like, so we separate V and W into corresponding X, Y, and then show that A and B can be represented by that?
Yeah, so, well, yeah, so you can, that's right. You know that V and W are elements in R2, so you know that they can be expressed like this. So V is equal to, let's say, V1, V2, where VI are just real numbers, and W is equal to W1, W2, where WI are in real numbers, right? And then you can express the equation AB is equal to lambda 1 times V plus lambda 2 W. So you could write this equation out. You can expand it out in terms of the coefficients of V and W, and then you have to solve those equations. Okay, so I think this is a good exercise. Try to solve. I'm not going to do it now because we are going to do it in class. We're going to do exactly this type of problem. Under the assumption that W is not in the span of V, right? If the problem is that if W were in the span of V, then the combinations of V and W would always lie in this line, and I would never be able to get this pink point, right? It's very important that W is not in the span of V in order for this to work. Geometrically, you should also be able to do it. You should be able to say, from this point, I should be able to draw a parallel line and parallel to the blue line. And I should be able to draw a parallel line to the green line. I'm trying to. Okay. And then you can see that we have this vector, and we see that we have this vector, and the sum of them gives this pink point. And we can see that this vector is some multiple of W, and this vector here, let me just draw them in yellow. We have a vector here. Oh, that's bad. We have a vector here, which is some multiple of V, and we have a vector here, which is some multiple of W. Okay, so geometrically, you can see that to solve it, all we need to know is the ratio of length along this line here between this point and this point, the given W and the given V. So you can see even in this picture, you can see that lambda 2 is going to be something like, I don't know, like 1.2, and lambda 1 is going to be like 0.6. So lambda 2 is somewhere around, 1.2. Lambda 1 is somewhere around 0.6, because 0.6 multiplied by V plus 1.2 multiplied by W is going to give me the sum of this vector, and that sum is AB. So the only thing is to do this exactly, using the actual entries of W and writing down the formula for what lambda 2 and lambda 1 are. You can solve explicitly for the formula.
Concerning, in the assignment, it says something like field of 2 elements to the power of 3. Does that mean that there will be 3, it'll be a 3 tuple? And we'll have to solve for that?
So, well, okay, I'm not sure what your question is, but what is f2 to the 2? f2 to the 2 is just all ordered pairs A, B, such that A and B are in f2. And you can draw that like this. You can draw it like that.
Okay, so then
this is f2 squared.
So
This is
f
0,
to the 3
0,
would be
1, 0,
3-dimensional in that
0,
case.
1, and 1, 1, right? So this is f2. This is the vector space f2 squared. It's a 2-dimensional vector space over the field of 2 elements. Okay, and this is kind of interesting because the vector space only has 4 vectors in it. It has these 4 vectors. That's it. There's no other vectors in the vector space. But you can add them together. You can do vector addition. You can do scalar multiplication by elements of f2. So it's like a computer version of 2-dimensional space. It's a digital version of 2-dimensional space. Very simple. Okay, and subspaces, you can figure out what they might be. You start with 0, the origin. That's got to be one space, one subspace. You can also have the whole space. That's another space, and then there's things in between. And so you can just go through what the spaces, the subspaces could be.
All right. Thank you so much.
You're welcome.
Have a nice day.
You too.
Okay, so Shivraj has a question.
Hi, sir.
Hi.
Today you
I don't
mentioned
think you've
that-
asked a question before.
I have. I just answered. I asked in the first few lectures.
Oh, okay.
Today you mentioned that there was a warning at the start of the lesson.
Yeah.
Can you just go to that?
It is here. Yeah.
Yeah. So you said if f is equal to r, it is valid to define
Yeah.
polynomials as functions.
Yeah.
Does that mean that if f equals f2 equals z2, that it's not valid? Would I be wrong in saying that?
What's not valid? What is it that you're asking about?
That only f equals r is valid. Is that true?
Yeah, but what is valid or not invalid? What statement is it that we're talking about here of being valid or not valid? You tell me what the statement is.
Because you said that it is not injective at the bottom of the page.
I understand, but try to tell me intuitively. What are we talking about? What is the warning? What is my warning really? Tell me what it is. Do you know?
That we may view a polynomial as a map.
Yeah. Okay. And what's the warning about that? About there's a relationship between polynomials and functions, right? I mean, you learned about polynomial functions, right?
Mm-hmm.
So a polynomial, it eats up a number and it spits out a number.
Yep.
Right. So my warning is about that. And so what is the warning?
That, well, I wasn't very sure about it. So that's why I asked.
My warning is that it's not true.
Okay.
That's what the warning is.
And so it can't be injective, right?
But wait, don't worry about injective or anything like that. You're assigning, you're getting into mistakes when you're trying to use the technical terms. So I'm trying to get the idea straight first, right? So it's very common to think of polynomials as functions. Okay, I hope that's clear. Like x squared is a parabola. Okay, it takes a number and spits out the square of the number. So it's very common to think of a polynomial as a function. This is polynomial.
Yeah.
Okay. But what I'm trying to say is that if you're not using the real numbers and if you're using one of our fancy fields, okay, then this idea breaks down. Because look at this example. Okay, I have a polynomial which is x squared plus x. Now, if I gave you, in high school, if I had presented you this polynomial, and if I asked you to graph it, what would you tell me? What would you give me as the graph of this?
Parabolic shape.
Yeah, okay, and what are the zeros?
0, 0.
There's 0, 0 is 1, 0, and what's another 0?
-1 and 1.
What?
A -1.
-1. Okay, and does it have a minimum or does it have a maximum?
A minimum.
Yes, thank you. So it looks like this, right?
Yep.
So you would agree that this function, the purple function, and the green function are different functions.
Yes.
Okay. What is the green function? Which function have I graphed?
X equals 0 or y equals 0.
Yeah. So the polynomial function, it's a polynomial function, right? It's the polynomial function 0. Okay.
Yep.
Whereas this one is the polynomial function x squared plus x. So you agree that these are different functions?
Yes.
Okay, but what if I was working in the field with 2 elements? Okay, then there's only 2 possible inputs.
Mhm.
Because the field of 2 elements, there's only 2 numbers in this world, 0 and 1. So
Okay.
0 squared plus 0 is equal to
0.
And 1 squared plus 1 is equal to
In this field, 0 as well, right?
0 as well. Why do you
Yep.
say right? Why do you ask? It's not an answer, it's a question.
Because we have only 2 elements in our.
Well,
in
okay,
this
so
defined
what's 1 squared plus 1?
0.
But why?
Because we only have 0 and 1, so there must be an additive inverse.
But go through it in detail. What's 1 squared? What's 1 times 1?
1.
In the field of 2 elements, that is right. And then you'd have 1 plus 1, right?
Which is 0.
Which is 0. So this means that this function only takes 0 values. It's the 0 function.
Yep.
So this means that if we believed that polynomials were functions, it would be correct to write that this is equal to 0. But it's not true. In the field of 2 elements, this function is the 0 function, but the polynomial is not the 0 polynomial. It is an interesting polynomial because the coefficients are perfectly nice, 1 and 1.
Mhm.
Okay, so I'm trying to warn you that there's a difference between polynomials and functions. Okay, polynomials determine functions, but it's possible that you could have 2 different polynomials which determine the same function. So let me explain. So this is, let me do it like this so that it's crystal clear to you. So we have polynomials and we have functions from F2 to F2. And these are polynomials with coefficients in F2. We have 2 different sets, okay? And I'm saying they're different. That's what the warning is. So for example, in these polynomials, I have the 0 polynomial and I have the polynomial x squared plus x. And I have the polynomial x cubed plus x squared plus x plus 1. Okay. And in here, I have many different functions. So the functions, let me think about how many functions are there. Well, the functions from F2 to F2, there's only 2 possible inputs and there's only 2 possible outputs, right? So if I graphed all possible functions, I would say, well, there's the 0 function, which takes 0 values on both 0 and 1. There's the function like this, which takes value 0 on 0 and 1 on 1. There's the function like this, which takes values 1 and 0, or there's the function like this, which takes value 1 on both points. So there are 4 functions. Let me call them F1, whatever. I don't really care how to label them, but I'll call them F. I want to use a darker green. So I want to call them F00, F01, F10, and F11. There's only 4 points in this space of functions. This I'll call F00. I'll call this F10, F01, and F11. It's not important, the labeling that I give. The point is that I have 4 functions. And here's the point, is that this polynomial, which function does it determine?
F2. Oh, you mean 0?
This function, this polynomial 0,
Yep.
if I evaluate it at these 2 points, what values will I get?
0.
0, 0. So the function that it determines is f0, 0.
Yes.
Okay, so that means that this is sent
To F00.
to f0, 0. Okay, what about this one? What's the values that this one takes?
0, 1.
No,
Oh no, 1, 1, 1, 1.
no. So evaluated on 0, what do you get?
0.
And evaluated on 1, what do you get?
Also 0.
Yes. So which function does it determine?
F00.
Correct. So it gets sent to f0, 0. And what about this function?
0, 1.
On 0, it has value 1. And on 1, it has value 0.
So it could be just 0, 1 and 1, 0.
So which function does it get sent to?
0, 1 and 1, 0.
So
It could be either
so
or.
what value does it take on 0?
1.
Okay, 1. And what value does it take on 1?
0.
Okay, so it's this function, which I called f10. So it's getting sent to this function. Okay, so what I'm trying to say is that polynomials and functions are different. Polynomials determine functions, okay, but it could be that you have 2 different polynomials which are sent to the same function, which determine the same function. And that means whenever you see something like this, whenever you see a map that takes 2 different things to the same thing, okay, that indicates that you have a failure of injectivity.
Yeah.
So the map from polynomials with coefficients in F2 to the functions from F2 to F2, that map is not an injection. Does that help?
Yeah, it really helps because now we can show that it doesn't work the same way as how we would expect originally.
Yeah. In the real line, this does not occur. That every polynomial determines a different function. And so you get an injection from polynomials to functions. Okay, I'll take another
Thank you
question.
so much.
Yeah, you're welcome.
Okay, so Dikshant has a question.
Hello. Yeah.
Hi, go ahead.
So in the assignment, you gave this, like in the last 2 questions, there's this weird symbol which I couldn't really understand what it meant. It's like a plus with a circle around it. So I just wanted to clarify what that really meant.
Oh, well, in the reading that will be explained.
The reading was chapter 1, right?
Yeah. Let me just check. So I'm just afraid that in case he uses a different notation, let me just check. Where is it? Okay. So if you look at definition 1.40 on page 21, that's where it's explained.
Oh, okay.
Now I can also explain a little bit what what is happening.
Yeah.
So, okay, so let's say that you have a vector space V, okay, and you have 2 subspaces. So you have 2 subspaces, let's say U1 and U2. Okay, so there's this notation which is u1 plus u2. Okay, and this is the sum, and it's explained on page, the previous page, on page 20. Okay, and the idea is, so don't be confused. U1 is not a vector. U2 is not a vector. It's a whole collection of vectors. It's an entire subspace. So what this notation means is that it's the set of all possible sums where the first element is taken from U1 and the second is taken from U2. So it's the set of all possible vector sums where U1 is in U1 and U2 is in U2. Okay, so for example, if I take this point and this point, sorry, this should go through the origin. It's just my drawing is not perfect. Okay, and if you add them together, you'll get U1 plus U2. Okay, but that's just one element. This is just one element in this sum of subspaces. Okay, in order to get the full set, you need to consider all possible sums where you let U1 range over all possible values in U1 and U2 can be anything in U2, and you get a huge set of possible sums. And the point is that this is itself, this is a new subspace. So this is an operation on subspaces. If it's like saying, if I give you one subspace and another subspace, I can add them together. Yeah, I can add them together and we get a new subspace. Okay, that's the, where is it? Yeah, that's like on page 20 and 21, all of this is covered. Okay. So in this case, for example, you can see that if it was R2, if it was just regular R2, and if U1 and U2 were these lines, then the sum of these two subspaces would be the entire R2. Okay, let me give you another example. Suppose that we were in R3, and suppose that we had one subspace was just, let me label these as X, Y, and Z. Suppose that one of the subspaces was the y-axis, and I'll call that subspace U1. Okay, so this is the span of 0, 1, 0. The 0, 1, 0 is this point right here, 0, 1, 0. Okay, and then the other subspace, I'll take it to be the plane, the XZ plane. Call that U2. And this is the span of 1, 0, 0 and 0, 0, 1. Okay, so I have a plane, I mean, we're gonna study this in great detail as the weeks progress, but what I have here is two subspaces of R3. Okay, and what happens if you take the sum of both these subspaces? That means that you have to take all possible sums where the first element is in U1, the second is in U2. Right, so if I take all possible sums, that means I'm gonna have elements like, you know, that means I could get any vector at all, right? Any vector in three-dimensional space, I can express it as a vector in U2 plus a vector in U1, right? So that means that when I take the sum of these two subspaces, I'm going to get all of R3. So in this example, U1 plus U2 is equal to all of R3. Okay, but on the other hand, what I could do instead is I could take a smaller subspace. I'm not going to change the vector space. It's still 3 dimensions. And so instead of U2 being the sum, the span of two vectors, I'll take the span of one vector, and I'll take that vector to be 0, 0, 1, just the z-axis. Okay, so now u1 is the y-axis and u2 is the z-axis. And if I take the sum of these two, okay, then I'm going to take all possible sums of the vectors 0, 1, 0. So let me put it like this. So u1 plus u2 is equal to the set of all possible sums u1 plus u2, where u1 is in u1 and u2 is in u2. Okay, and this, I can write it explicitly. I can write it as the set of all lambda 1 times 0, 1, 0 plus lambda 2, 0, 0, 1, where lambda 1 and lambda 2 are in R. Okay, and if I simplify that, I get the set of all 0, lambda 1, lambda 2, right? And so you can see what that subspace is. It is exactly the YZ plane. So I get all of this. But I do not get all of R3 as this sum.
Yeah.
Okay, that's the idea of sum. Okay, but on the next page after 20, it's page 21, talks about the sum with the circle around it. Okay, so what about U1 direct sum with U2? This is called the direct sum. Okay. And this is a slightly confusing notation, but what it means is that this is a, you should read the page 21, but this is it's a feature of the sum. So this is saying, when you see this, it means that you're taking the sum of the two subspaces just like we did before. However, it's telling you something special about that sum. It's saying that U1 and U2 are such that when we take this sum, so putting a circle around the plus, okay, means that, I just want to make sure that I'm not gonna, yeah, it means that that each element in the sum can be written as U1 plus U2 with U1 in U1 and U2 in U2, okay, but in a unique way. But for unique U1 and U2. Okay, so if we look at this, okay, we said that U1, remember U1 was the y-axis and U2 was the z-axis. And the sum of the x-axis, the sum of the y-axis and z-axis is giving the yz plane. Okay, but now look at one of these elements in the yz plane. We know that given an element in here, then there's all, this is in the sum, so I can definitely find a point in the y-axis and a point in the z-axis, so that the vector sum is this point, V. But the point is that this pair, U1 and U2, U1 and U2 are unique with, they're unique. There's no ambiguity about choosing them. It's not possible to express V as a sum of U1 plus U2, except with these particular values of U1 and U2. Okay, so that's what I mean, that it's telling you something about the sum. It's telling you that the sum is direct. Direct means that there's only one way to write each element as a sum of elements, one from the first and one from the second. this sum is also direct. It's also direct. This is direct. So I just want to give you an example of a sum that is not direct. Okay, so let's say that we take U1 to be this line. Okay, and let's say that U2 is also this line. Okay, then it's true that U1 plus U2 is the same thing as U1 or is the same thing as U2. So the sum is perfectly well defined. I just take all possible sums where the first vector is taken from U1 and the second vector is also taken from U1. Okay, so when I take all possible sums, what do I get? I don't get anything more than what I had when I started. I just get U1. Okay, but this sum is not direct. Right? Because, for example, if you take a vector, I can write it as 0. I could write it as I could write it as, you know, v plus 0. I could write it as 0 plus v. I could write it as 1/2 v plus 1/2 v. Right? There's many, many ways that I could write that element in this case. So it's not unique. It's not a unique decomposition. So this is not direct.
Yeah, that makes sense. Thank you.
Okay. Okay, so we're running out of time. For the people left who want to ask questions, try to think about whether your question, you could ask it on Piazza or in your tutorial. Yeah, of course, everyone knows that there's another tutorial opening up today from, what is it, from 2 to 4? Can anyone confirm that? Is that right?
Yeah, 2 to 4.
Yeah, 2 to 4. And you should have received the notice in your Quarkus. So try to think whether you can ask the question there. But if you really have to ask it to me, go ahead.
Yeah, I'm just kind of sure. Like I read this book before, like the linear algebra done right. So I have already like a perception of that everything has to be explained as like a linear dependence or independence. Like everything has to be like a x, y, so axis and x2's axis. So I have a hard time to understand like voice function space in that mindset. Like it seems like cannot break that into like linear dependence or like how the axes go and how they transform. Like there's sort of like the perception like become an obstacle for me to understand those things. So I wonder if you can like explain it like in like the linear dependent independence way.
But we haven't talked about, we're not there yet. We haven't gotten to linear dependence and independence yet.
Yeah, but because like I read a book before, so
yeah,
I
but that's your problem.
Everything.
But that's your problem.
But yeah, so yeah, I guess.
You're reading ahead. That's very good. But
yeah, but
the fact that you're reading ahead means that you're going to encounter things that are confusing, and that's normal. So you just have to wait because we haven't gotten there yet.
Okay, so
right now what you need to do,
point,
just one second.
Okay, yeah.
Just 1 second. So right now what you need to do is make sure that you understand why function spaces are giving examples of vector spaces and how they work. That has nothing to do with linear dependence and linear independence. Okay, yeah. So you have to make sure that you understand the material that I'm covering now, right? And don't worry so much about other things which are confusing you, because we're going to get to those later.
Yeah, I just wondering because it cannot get into my system. Like it's like outside.
Well, that's a problem. That's a problem. You can't screw yourself up by trying to incorporate everything at the same time. You have to go bit by bit and build your knowledge. So my advice is to make sure that what I'm talking about now, ignoring completely the other stuff in the book, is making sense.
Okay.
Okay.
Yeah.
Because if you miss that, then you're going to be behind. You're going to be very, very far behind by the time we get there.
Okay.
Okay. Someone else. Shizuo.
Yes,
Well,
I have a question.
yeah, go ahead.
And you have just introduced the difference between the polynomial as where x as a symbol and x can be element in a
Yes, yes. There's a difference between polynomials and functions. Yes.
yeah. And I have a question. And if any polynomials is distinct in uh, a certain field, is that means that this field should be real number?
Well, so you're asking about whether this theorem is true. So the answer to your question is no, it is not true. Okay, so you should think about other fields where it may also be true. But the answer is no, it is not true that the fact that polynomials, the map from polynomials to functions, if that is injective, then the field must be the real numbers. No, it is not true. And you can easily see that just by going through some examples of fields that we studied already. So just do that work yourself.
Okay,
Okay.
Thank you.
Okay, Diba, can you quickly go with your question?
I think it's pretty quick. The only
Yeah.
thing I don't understand is the second diagram on the function space f cross f. So the one that's like the Cartesian plane, I understand why that's analogous. I don't understand why the second one is.
What, this?
Yes, that one.
So function, this is a function on B2.
Yeah.
And I'm drawing a picture of it. What is this picture? The picture is simply the graph of the function. I have the domain, which is a B2.
Okay.
And I have the codomain, which is R.
Okay.
And I've drawn the graph of the function. It takes a certain value on the point 1. It takes a certain value on the point 2.
Yeah.
This is the graph of a function. It's just not sine or cos. It's a function on just 2 points.
Okay, I completely misunderstood. I thought that was supposed to be the same thing as like R cross R, which is.
But it is the same because you see that a function on 2 points has 2 values.
Yeah.
Right? A and B.
Yeah.
And if you put those on a list, you will get an ordered pair, A, B.
Yeah.
So it is the same thing as a point in the plane.
Because you need 2 discrete pieces of information.
Correct. Correct. Okay. And not only that, but they're ordered.
Yes.
You first put the value on 1, and then second is the value on 2. Yeah. If there was not an ordering 1, 2, then you would not know which one to put first.
Right.
And it would not be the same as an ordered pair in the plane.
So these elements of f to the n are just ordered n tuples.
Correct.
Okay.
I mean, tuples are automatically ordered. You don't need to say you don't need to say ordered n tuples. A tuple is a list, and a list is always ordered.
Okay.
Yeah.
Okay, then I'm good.
Okay. Arkaprava?
Yeah, so this is more of a technical question regarding the assignment.
Go ahead.
In question 3, you have defined a relation between V and subspaces of T. So I was wondering whether the V used over here is actually the subspaces that we found in question 2, or whether V is actually F5.
Well, what is V? Sorry, what is V?
One second.
Sorry,
it's not open right now. Sorry.
I just need to look at.
So it says let V be a vector space and T a subset of V, a linear subspace. Define an equivalence relation on V as follows, and so.
What was the name of the subspace?
An equivalence relation on V as follows: vectors x and y in V are equivalent modulo T when x minus y is belonging in T.
T, yes. Yeah. Okay. So T is a subspace of V. Do you agree that T is a subspace of V?
Yeah.
Okay, and in the previous question, you studied subspaces of V, correct?
It didn't specify it was V. It just said find linear subspaces of 2 different.
Yeah, but you studied in the previous question. You studied vector spaces, and you listed. You studied the subspaces of that, right?
Yeah.
So those would qualify as T. That's what you can use as T. If you found all of them, then those are the possible choices for T.
Oh, all right then. Oh, thank you.
Okay.
That clarifies it.
Okay, she, go ahead.
Sorry. So my question is about how to comprehend the idea of the vector space of all real value functions.
Yes.
So would it be like any vector would be just a vector space of R squared? Would that be a good analogy or something like that?
Sorry, what is the vector space? We're talking about a vector space of real valued functions on the real line, right?
No, the vector space I'm talking about is R to the power of R.
Okay, but what does that mean? What does R to the power of R mean? That's a fancy notation for something very simple. It's just all functions on the real line.
So it's a set of all maps from R to R?
Yeah.
So
correct.
What would one single vector be like?
It's a function from R to R, a function like x squared or sine x. Those are vectors.
Can we understand it as spanning and rotating one vector, which is R squared?
I don't know what that means. That doesn't make sense. The point is that every single function, even if it's not continuous, every single function from R to R is a vector in this space, okay? It's a very large vector space. It's highly infinite dimensional. It's not possible to really visualize it because the number of independent directions is infinite.
And we cannot really describe the direction in that sense?
Well, what do you mean? I mean, you know very well what the functions on the real line are. You studied them a lot already. So you know very much this vector space, you just don't think of it as a space where the points are functions, right? But I'm just saying that it is possible to think of it that way. You could think of every single function as a point in the space of functions. And the nice thing is that that space is a vector space over the real field.
Okay, got it. Thanks.
Yeah. Okay, last question, Kanishk.
Yes, sir. I had a question regarding what you re-explained right now, just a moment ago, about R2, the subspace we were talking about. We talked about linear combination there. So I had a question regarding that.
Yeah, okay.
Yes, sir. So we kind of said here that the span of V vectors V and W can be lambda 1 V plus lambda 2 W.
Yeah.
So can we say that if we take any two vectors, any vector actually, it can be expressed as a linear combination. Rather, I will rephrase my question. I want to say actually that can we say that any vector can be expressed as a linear combination of two vectors? So it lies in the same space. These three vectors lie in the same space.
So I gave a discussion of this problem after, okay. So there was a question about whether the span of the W and V together is R2. And in order to show this, we needed to show that for any vector in R2, we can express it as a linear combination of V and W. Oops, sorry, that should be W. Okay. So I explained how to approach this problem. And the challenge is to show that any vector whatsoever can be expressed as a linear combination of V and W, as long as W is not in the span of V. And V was chosen to be non-zero.
So if we take for say higher dimension, so can we say that a vector can be expressed as a linear combination of some other vectors, maybe more than two?
So Kanishk, we are getting to that later. We're not there yet.
Okay,
So
I'm
linear
sorry.
combinations and linear independence is coming later.
Okay,
So just
thank you, sir.
postpone your question for later.
Thank you, sir.
Okay, everyone. Have a good weekend and consult Piazza and have fun at the tutorial. Thanks a lot, Syed.